I'll be talking about global chiral symmetry and extra dimensions and topology. This is sort of a relatively completed subject, so this will be a more pedagogical lecture. So this is something I know a fair bit about. Tomorrow I'll be talking about something I just know something about. Saturday will be quantum computing, which I know very little about. And then this workshop will be mercifully over before the progression can be finished. So, chiral symmetry. Chiral symmetry plays a really important role in particle physics. It's global chiral symmetries here. They protect theory from fine-tuning of fermion masses, for example. So before the Higgs was found, there was a certain logic to the fact that the only particles we had seen were gauge bosons, whose masses are protected by gauge symmetry, and fermions, whose masses are protected by chiral symmetry, so that when they get radially corrected, it's only logarithmic instead of linear, the way it looks like it should be. And that could then easily explain why you might have a hierarchy up to the Planck scale without any fine-tuning or any extra physics. Along came the Higgs and changed that, but still, the chiral symmetry is very important for understanding how the masses and Yukawa couplings of the standard model behave. Furthermore, the approximate global chiral symmetries give us the whole picture that Nambu gave us, which is that the pseudoscalars are Goldstone bosons of the broken chiral symmetry. And then finally, chiral symmetry is required for standard models and guts and all sorts of beyond the standard model theories when they become gauged. And so it'd be nice to understand how to realize these types of symmetries in a lattice theory so we could do non-perturbative physics. So in this talk, I'll be talking about the global chiral symmetry case. So if in general, you have some sort of action with some sort of fermion operator on the lattice, which I wrote here in momentum space. It is on a lattice, you've got a finite momentum space there. Then the famous Nielsen-Namiya theorem says you can't have all four of these properties that you would have considered to be desirable. You want to have D to be periodic and analytic function of P. So for example, the types of problems you might have if there was a discontinuity in P and in D as a function of momentum is that there's a word identity that tells you that the coupling of the gauge boson to a fermion is proportional to the derivative of the inverse of the propagator. In other words, the derivative of D with respect to P. And so if you have a discontinuity in D of P, you would expect some horrible strong coupling at some point on the Brillouin zone, the photon. Then, of course, you'd like to have the correct continuum limit that looks like a Dirac fermion for long wavelengths. You'd like it to be invertible everywhere except for P equals 0, which is a statement that you only have one flavor in the continuum. Remember, in Euclidean spacetime, the pole for a massless fermion is only at P equals 0 in the continuum. And then finally, you'd like to have the chiral symmetry where gamma is the analog of gamma 5 in whatever dimension you're in. And of course, we know that gamma 5 is only defined in even spacetime dimensions. So Nielsen-Namiya says you can't have all four of these at once. And so the natural thing to do on the lattice is to break the chiral symmetry because that seems like the least drastic thing you can do. But of course, you pay a price. Now chiral symmetry is explicitly broken, and so the way we understand the anomaly is that you put in a theory like, say, Wilson fermions, got explicit breaking with a mass term, explicit breaking with a Wilson term that gets rid of the doublers. And now these both violate chiral symmetry in a big way, and you have to fine-tune them to make it go away and get massless pions. And in the process, you find that the fine-tuning does leave behind a ghost of the chiral symmetry breaking in the form of the anomaly. However, this does require linear fine-tuning, namely order 1 over A, in order to get to the symmetric point. Furthermore, besides breaking the U1 anomalous symmetry, it also breaks the anomaly-free flavor symmetries, such as, for two flavors, the chiral SU2 left cross SU2 right. So what I'll be describing today is the minimalist way to explicitly break the symmetries, in that it'll be domain wall fermions and overlap fermions. And these two have the feature that there is no, what do you call it? I forgot the word, sorry. You don't have any casualties other than the exact amount of symmetry breaking you need for the anomalies. And furthermore, you find that you don't have a fine tuning like you do for the Wilson fermions because of the topological nature of how these work. And they also are an interesting starting point then for discussing chiral gauge theories, which I'll talk about tomorrow. So the starting point for domain-wall fermions is you consider, stick to 2+1 dimensions because I can draw pictures there better. So I'm going to look at a Dirac fermion in 2+1 dimensions where the two spatial dimensions are represented as the cylinder, and this extra dimension, I guess I call it x3 elsewhere, the extra dimension is compactified. And furthermore, on one side of the universe, you've got a positive mass for the fermion, and on the other side, you have a negative mass. So x3, okay. So, and on top of that also, there are gauge fields, but the gauge fields are entirely two-dimensional, namely 1+1 dimensional gauge fields. They don't have a component in the third direction, and they don't depend on the extra coordinate. So you just have an A1 of x1 and x2 and an A2 of x1 and x2. Nothing, no A3 and no dependence on x3. So it's useful to take the fermion field in the extra dimension, since you now have a separable system, since the only place where x3 occurs, in the continuum currently, is through the Dirac operator, the d3 gamma 3. So it's useful to expand this in the following way. What I've got here are parity projection operators, where this is the 1+1 dimensional parity operator, which is 1 plus or minus gamma 3 over 2. I've got some spinors corresponding to the 1+1 dimensional Dirac theory, which I haven't specified yet. And then I have a bunch of functions of this extra coordinate. There should be an I there also. They are labeled by n and I will denote the parity under the x3 to minus x3 symmetry when I've cut open my cylinder here. So I guess 1 is even and 2 is odd. And then n will be the whole tower of modes that I get when I look at eigenfunctions here. Now, in particular, I'm going to choose a complete set of eigenfunctions, b and f, to be solutions to a particular eigenfunction equation. Namely, they'll solve this following set of equations, which is sort of a supersymmetric quantum mechanics problem, where this operator q, which is like the supercharge, is the derivative with respect to the extra dimension minus the space-dependent mass term. So I called these things b and f in analogy to boson and fermion, but of course, they're just functions. Oh, this should have been an f. I apologize. So when you compute the spectrum, what you find is you get a bunch of tower states. You find that you get these two special states here, which correspond to eigenvalue equals 0, and these are exponentially falling or growing modes. The way to think about this is a mode that's localized around x3 equals 0, and this one, which is growing, is actually localized next to the other boundary, namely x3 equals L. And these are just normalization factors. Okay, and they only come in this positive parity combination. And then you get a whole bunch of bulk modes that correspond to cosines or sines. They are absolute values of x because of the absolute value, because of the shape of this mass function. And these correspond to modes with eigenvalues that look like k squared plus lambda squared. Lambda, remember, is the height of the value of the mass in the bulk, and kn is just the usual n pi over L. So the important thing, though, is you find these exact zero modes localized at x3 equals 0 and x3 equals L. Now, these are actually exact zero modes, even though it's a finite space, and the exactness is due to the fact that this mass function integrates to 0 as I go around the circle. This is not protected. Later, when I introduce interactions, that can change, and I'll discuss that. But it's useful for solving the problem to use the special case. In particular, what you find, though, is that if you remember that the B is going with P minus and the F is going with P plus, and so what we see here are that the B mode here corresponds to a left-handed mode in the 1+1 dimensional theory, and the F will correspond to a right-handed mode. So here's the picture then. You've got this localized state here and a localized state at the other, on the other edge. And if you look at the spectrum, here's the supersymmetric spectrum here. You have degenerate states for both B and F. Now let's plug this back. Now that I've done this expansion, let's plug this back into the three-dimensional action. So you take this expansion and you plug it into this action that we have here, and it, because of the orthogonality properties of B and F, you end up finding that you get a sum over modes with this set of basically an infinite tower of 1 plus 1 dimensional Dirac fermions with mass mu n. But the important thing is that for the case n equals 0, the left and right-handed modes, it looks like just a massless Dirac fermion, but you have to remember that I've integrated over this extra dimension, but you have to remember that their wave functions are localized far apart from each other. As a result, then, if you want to compute a perturbation, say from a gauge boson loop or something like that, first order perturbation theory, you want to ask how does that affect the zero modes? Any perturbation is going to require the overlap of any chiral symmetry violating perturbation is going to require the overlap of the left and right-handed modes, and their wave functions have exponentially small overlap. And so you're guaranteed that these things will be suppressed by e to the minus 2L. So that makes this thing look rather robust, and in particular, in the L goes to infinity limit, a theory with exact chiral symmetry. Now, you have all these bulk modes you don't want, so what you can do then is you can throw in a Pauli-Villars field, which has exactly the same action, except for the mass, instead of having a step function, is just constant. Now you can go through the same procedure, expand this capital phi in terms of B and F modes, but because this lambda is constant, you find that you get a different set of eigenvalues. They are exactly the same for all the non-zero values for the original fermion, but instead of having a zero mode now, you end up with eigenvalues at lambda. So when you put this theory in, all this infinite tower will cancel, and you end up with a theory of one massless chiral fermion and one heavy flavor Pauli-Villars in the two-dimensional theory. So what about the anomaly, though? So your 3D theory has no U1 anomaly. Currents that are conserved classically are exactly conserved completely. So, but on the other hand, the edge states describe an effective 1 plus 1 dimensional theory, which should have an anomaly. So here, this is the same picture I showed yesterday. Here is the dispersion relation for the fermions on the edge. And you know that if you turn on an electric field, you have to have a change in number of right-handed modes on one wall and left-handed modes on the other. So this was answered by Callean and Harvey in the mid-'80s. They were interested in, string theorists have always existed, even before the invention of string theory. They used to do monopoles and defects, and then they did anomalies, and then they did string theory. And so before the first string revolution, everybody was doing anomalies, and there were all these descent equations, anomalies in different dimensions. And people weren't trying to understand that, and Callean and Harvey had a nice physical picture for how anomalies worked related in different dimensions. And the way they did it was they analyzed the Dirac equation in the presence of various types of defects. In particular, they showed that if you have the fermions if you take a fermion in 3 dimensions and you integrate it out, a massive fermion, the thing that's really interesting in 3 dimensions is that there is a marginal operator, which is not the usual, you have a marginal operator, which is the Chern-Simons operator, and the fact that it's marginal means that the resultant operator, when you integrate out a massive fermion, it cannot be suppressed by the fermion mass, because the coefficient of this operator has to be dimensionless. And so you have this remarkable effect where heavy fermions, when integrated out, do not decouple. In particular, however, there's something curious about this. If you look at the Chern-Simons operator, it's got an epsilon tensor, and it violates parity and time reversal. And you might ask, well, how can a Dirac fermion, when integrated out, violate parity and time reversal? And the answer is that in odd space-time dimensions, a fermion mass violates both P and T. It has to do with the fact that while in 3 dimensions, changing the sign of x, y, and z is a parity transformation, in 2 spatial dimensions, changing the sign of x and y is not a parity transformation, it's a rotation. So instead of having a gamma 0 in the parity transformation, you have to have a gamma 1 or a gamma 2, and that will make the mass term flip sign. So when you integrate out a fermion, the sign of the mass flips under parity, so that means that you can get this Chern-Simons term as long as it is proportional to the sign of the mass. And so the mass of the heavy fermion does come in, but only as its sign, not as its magnitude. And so you get 2 contributions, one from your fermion and one from our Pauli-Villars field. And in front of these operators. And this is what the operator is in D equals 3, and this is what it is in D equals 5 for U1 theory. For non-abelian theory, you have extra pieces. So if you now forget for a moment that I don't want to put in a gauge field pointing in the 3 direction, but put in a general gauge field for 3 dimensions, and then differentiate with respect to that gauge field, you find a current. This is the Callean and Harvey current, and in particular, if I put in this 3-dimensional Chern-Simons term with this coefficient, then when I differentiate with respect to A3, I get a current in the 3rd direction, which is proportional to epsilon 3ij, which is just the 2-dimensional epsilon tensor, with the diaj, where these indices now are just over the 1 plus 1 dimensional indices. And furthermore, you have a coefficient that is proportional to this here, which is just an epsilon, a sign function for the fermion, and a 1 for the Pauli-Villars field. So notice that this adds up to 2 on one side of the defect of the cylinder and 0 on the other side. Actually, Callean and Harvey forgot to put in the regulator, because the graph itself is finite, but there are other graphs in the theory that are not, and you have to have a regulator. When you put in the regulators, they also don't decouple, so you can't ignore their contribution. So Callean and Harvey got the incorrect answer of having half a unit of current coming in from both sides, when in fact it's really 0 current on one side and twice the Callean and Harvey value on the other. So the important thing is that this current has a divergence at x3 equals 0 and at x3 equals L. But only in the presence of a non-zero electric field in 1 plus 1 dimension. So you find that charge and chirality violation at each surface is consistent with the 2D anomaly, while the total charge and current is conserved in 3 dimensions. So what happens then is you turn on your electric field, you'll generate, say, a current going down here and a loss of charge on one wall, get a current going up and a gain in charge on the other wall, and then you have this bulk current that goes across, which is this J3. This is really remarkable, and it has to do with the fact that, again, that this is a marginal operator and that the heavy fermions don't decouple. It's remarkable because I can put in a current with an arbitrarily low frequency here, and I will get, if I can put in an E field with arbitrarily low frequency, and I'll get currents with arbitrarily low frequency traversing this bulk region, even though this region is gapped. And there's no mode that lives inside this region with a mass less than lambda. So this is sort of magical. And this is also none other than the Hall current in the condensed matter system. It's possible, as I said, because the mass term in 3D violates the 2D chirality, as well as time reversal, as well as parity. And because of this epsilon plus 1, there's no current on one side. And so, in fact, you can take this model and you just cut it off here and get rid of half of this. And so instead of studying a cylinder, you can get the exact same physics on a strip with 2 surfaces. And so, in fact, in the lattice formulation, while I first suggested this periodic case, Shamir realized that it was a waste of space to have this side here going along where nothing happens. And so now no one does the periodic case, they do the strip. So this seems really well suited for discussing chiral symmetry on a lattice, where you replace the scale lambda with 1 over the lattice spacing. The reason is because this 3D theory completely breaks chiral symmetry explicitly. There's no question of trying to get around the Nielsen-Ninamiya theorem. You're putting in you're getting rid of one of the 4 things they said you had to get rid of, and so you're fine there. And the result is very robust, because it seems like what goes into the existence of the 0 modes is just the fact that the mass is positive on one side and negative on the other. And so you can make it wiggle, you can shift it up and down. There's a lot of room to change this without changing the fact that you have localized modes on the surfaces. The drawback, however, of course, is that if you want exact chiral symmetry, you need infinite L. So then the first thing I did was put this on the lattice with naive derivatives, and I found that the progress I had made was that instead of 2 to the d doublers, I had 2 to the d plus 1 doublers. So that was a step backwards. But, you do what you can, and you say, well, okay, I'll throw some extra pieces in. I'll do what Wilson did. I'll add this term. So you might think then that this, of course, destroys chiral symmetry, but it doesn't any more than the mass term does. This is the same structure as the big mass you've already put in the theory, so maybe it's not so bad. In fact, there's a reason to think that it's fine. So if you add this Wilson term, you can sort of think of this as a wave function dependent mass term. It goes like k squared. So if I had a mass step function looks like this, it's small k squared, I get 0 modes because it's negative one side and positive on the other. Go to slightly higher k squared, and for those modes, I have a shifted domain wall mass term like this. And now what you'll find is that the mode is more tightly constrained on one side of the defect, but gets more delocalized on the other. So these modes are sort of reaching out towards each other, but still they're localized, they're exponentially localized. So this is okay. But if you go to a large enough k squared, now the mass is positive everywhere. There are no localized modes. These two modes on the opposite sides on these two defects can now join up and become heavy and lift their eigenvalue. This is a continuous process if you're on a finite volume. If you're at an infinite volume, it looks magical, but you have all the way up to some critical value of k squared, you have absolutely chiral fermions because you have exponential localization. And then all of a sudden you delocalize them and boom, they're gone. So I asked my graduate student to plot out what exactly the spectrum was. I just took the simplest solution when I first wrote it down, but I knew there were more complicated ones. And so he generated this graph with Carl Janssen. This shows the following. This is the Brillouin zone in 1+1 dimension. So this is a graph of px along the horizontal axis and py on the vertical axis. And the code is that if you have a chiral mode, it's white, and if you don't, it's black. So you start off, okay, and it's a function of m over r, where m is the height of the step function mass term, which we typically will set to 1, and r is the Wilson coupling. Well, actually, typically you set the Wilson coupling to 1 and change m. And so what you find is that if m over r is 0, or actually anything negative, you get no chiral modes. As you turn on m over r, you start getting a window of this region where there's a space where there are chiral modes, and then once you hit this edge of from the white to the black, you've reached the critical value for which they delocalize, and because this is an infinite lattice, you suddenly have absolutely no chirality, and so you have this discontinuous edge. As you increase m over r, this region grows until at this critical value of 2, all of a sudden you're touching these two corners of the Brillouin zone here. And as you increase it further, the area that where you had a chiral mode in the beginning at p equals 0 is gone, and now you have them at pi over a, either in the x or the y direction. And as you continue to increase it, those points eventually go away, and your new one opens up at pi over a comma pi over a. In other words, the other critical point on the Brillouin zone. And then as you increase m over r more, that region shrinks until finally, for m over r bigger than 6, you've got no chiral modes. And to make it even more interesting, the chirality of these modes switch. So for m over r negative, none, between 0 and 2, you get one right-handed mode, 2 and 4, you get two left-handed modes, 4 and 6, you get one right-hand mode, and so on. And then you run out. And you go to higher dimension, you just get the what do you call it, the magic triangle numbers, Pascal numbers? Forget. So when you actually look at a phase diagram and you plot m over r versus the gauge coupling squared, so here's the plot for Wilson fermions. This is a 5-dimensional version of
question. Why is it happening at 6 on the previous slide?
Sorry?
Why is it happening at 6, the number 6, on the previous slide?
Sorry, what's
the last plot there?
Yeah.
So why 6 is relevant?
Why is 6 what?
The ratio. Why is it 6?
Why is it 6?
Yeah.
Well, every 2 it changes and it goes through these numbers. I mean, it has to do with the fact that you're looking at whether 1 minus cos. I mean, basically, what you're trying to do is every time chiral mode appears or disappears is a place where there is an exact 0 in the Wilson propagator. Okay, and above m over r equals 6, there can't be any zeros anymore. So the picture then for Wilson fermions is typically looks something like this. This is 1 dimension higher than people normally look at it, where this is the so-called Aoki phase, where you have parity violation. Okay, and usually what you want to do is you want to go down towards 0 g squared, because g squared equals 0, because that's the critical point for non-abelian, Gaussian critical point for non-abelian gauge theory, and you want to tune it down to this point right here, where the continuum theory is defined right at this phase transition. For domain-wall fermions, it's quite different. You definitely do not want to have long correlation lengths in the bulk, so you're far away from a phase transition. You sit firmly within these different regions here, and the chiral fermions exist for each one of these x's. And in this case, you have 1, 4, 6, 4, 1 chiral fermion for those different choices. So I was sort of pleased with this picture. Then Martin Golterman came to visit, and he says there's something wrong here, because as you change your chiral modes discontinuously on the walls, then you're going to have to change your current, your Chern-Simons current. In particular, the coefficient of the Chern-Simons operator has to change discontinuously as I change m over r to account for the anomaly correctly. And how in the world could it do that? Because after all, the coefficient of the Chern-Simons current is just the result of a one-loop diagram, and one-loop diagrams don't jump from one integer to the other. So that was very puzzling. So we decided to compute it. And the problem is you want to compute it in a way that does not depend on perturbation theory, does not depend on any assumption for what the fermion propagator, or very weak assumption what the fermion propagator looks like. So we assume that there's some fermion propagator S of p, and then we can use the Ward identity to relate the photon vertex to that. So the photon vertex then is just the derivative of the inverse propagator. And now you take this diagram, which has a lot of physics in it that you're not interested in, and you want to pull out the Chern-Simons term, which has an epsilon tensor, and it has one momentum factor for all but one of the gauge bosons. So as usual, if you want to pull out n powers of momentum, you have to differentiate your integrand n times the momentum. And when the dust settles, the piece that you want has the structure. We have a trace of two n plus 1 factors of s ds inverse, where the derivatives are not with respect to space, but with respect to momentum. Now this looks very suggestive. Anybody who's looked at topological objects before, because it looks very much like a 2n plus 1 form. Because first of all, there's an epsilon tensor. You remember from general relativities that epsilons all occur with 1 over root g's, and measures always occur with root g's. So whenever you have an epsilon, the root g's cancel, and your answer is independent of the metric, which means it's not a geometry issue, it's a topology quantity. Furthermore, this here is typically, if S is some map that lives in some Lie group, then this is the differential element of the Lie group, and so this here is just some sort of volume element over the Lie group. So in fact, if you make some rather bland assumptions about the propagator, here's the inverse propagator. I'll say it's some function of p times a unit matrix plus some vector function of p dotted with gamma matrices. So we'll say that that is the general form for the fermion propagator dictated by Lorentz invariance. And you can now pull out a normalization, which is the square root of a squared plus b squared, and you're left with this unitary matrix here. So that's a number, function of p, times this unitary matrix. Now this number here is going to cancel out at this expression here, as long as n inverse is well defined. So as long as this inverse propagator does not have a zero, this n plays absolutely no role in here. And so it just becomes, this S really does become a Lie algebra valued object. And you find then that this is a winding number of a map. And the map is from the place where the momentum lives, which is a torus, that's the Brillouin zone, to the structure of this that you find in here with this theta vector, which lives on a sphere. And this winding number is an integer. And this integer cannot change as I change parameters in the theory until the basic assumption I made, which is that n of p is non-zero, is violated. And n of p is 0 at the special points where the bulk fermion is no longer gapped. And so you can then stick in the Wilson propagator as a specific example, and you find all of those numbers popping out at exactly those values of m over r, integer multiples of 2. This is actually one of the papers I'm most proud of, and it's sort of irritating that the condensed matter physicists don't look at it. Because it is the basis for the topology and topological insulators. So the conclusion is chiral zero modes are topologically protected. The topology lies in the dispersion relation in the bulk of the bulk fermions. So this explains how you can have topology on a lattice. It's not the discontinuous space that's giving you the topology, it's the continuous momentum space, which is of course only true on an infinite lattice. If you go to a finite lattice, this topology isn't quite exact. So as mentioned, this is the same thing that topological insulators discussed by condensed matter theorists. This is my view of condensed matter theorists. Okay, so what about what to do with the extra dimension? You can work at large, finite, not fine, L. You'd like to have infinite L, but of course, it is difficult to work at infinite L on a finite computer. So the other thing you'd like is, I was very happy with this picture because this is a nice effective field theory picture. You have gap fermions, and then you have low energy chiral fermions. But effective field theory is not something that everybody is totally familiar with. So a lot of people ask, how good is this chirality? How do I quantify it? And it's true that you'd like to have some better analytical handle on the effective theory after the heavy fermions are integrated out. And so you'd like to have a better analytical understanding exactly how chirality is obtained in this. And all of these questions could be answered through the really brilliant work of Neuberger and Narayanan with the developed overlap fermions and the related Ginsparg Wilson equation, which I'll get to now. So Neuberger and Narayanan wrote a series of papers that go from extremely obscure to eventually clearer and clearer until just crystalline clarity after about 6 years. And so since the early papers were long and confusing, because they were confused, a lot of the work was put aside until, wasn't paid attention to until suddenly, finally, there was this 2-page paper by Herbert that was just mind-blowing. So the idea that they started with is they said, let's turn this on its side, and we're in Euclidean space-time, let's call this extra dimension time. And then they said that the partition function then can be viewed as an overlap between the vacuum in the far past and the vacuum in the far future, where I've got a time-dependent mass going through a step function. That was the original way of thinking about it. In that picture then, but in the end, what it turns out is all you're doing really is you're integrating out all the heavy modes and asking what is the effective theory for the light mode. You can use their insight, though, about time, though, to express the effective theory D in terms of of a transfer matrix, where I think of evolving the fermions along this direction here, and that transfer matrix will involve the Wilson Hamiltonian from the 5D theory. So with the formula that Neuberger was able to derive for finite system was that the D ended up being 1 plus gamma 5 times 1 minus the transfer matrix to the L, where L is the number of steps, and divided by 1 plus T to the L. And this sort of peculiar structure comes from the fact that you've got not only the bulk fermions, but you also have the bulk Pauli-Villars field, which is coming in with the opposite sign, and that gives you this ratio here. And then you take the limit that L goes to infinity, and what you find then is that this T being e to the minus h, you find that if the eigenvalues of h are positive or negative, depending on which one they are, this T either goes to 0 or infinity, which means that you end up getting a sine function here, namely you just get 1 plus gamma 5 times the sine function of h, where h is the Wilson Hamiltonian. I consider this to be one of the most beautiful equations in physics. It tells you that somehow we're going to get Dirac fermions by 3 different matrices whose eigenvalues are just plus or minus 1. Unit matrix, gamma 5, and the sine function. All of the non-trivial dynamics that make up the world come from the fact that the gamma 5 and epsilon of h are not diagonal on the same basis. And that mismatch is completely due to the gauge field. So here's the overlap operator. You could write that sine function h over the square root of h squared. H is roughly, it's what you would expect from the Hamiltonian from a 5-dimensional Dirac theory where you have this extra Wilson term. So it looks like gamma 5 out in front instead of gamma 0, and then d slash plus m plus d squared. And this is a Hermitian operator. And so if I look at this object over here, if I call that V, you can easily see that V dagger V is 1. So it's 1 plus a unitary matrix. So that means that while the convention, in the continuum, the eigenvalues of d slash lie along the imaginary axis for a Euclidean operator, the overlap operator lies on a circle centered at 1. And furthermore, in the continuum limit, all of the eigenvalues you want from the real continuum d slash are located right here, where this circle looks sort of like a vertical line. So the overlap, sorry, did this wrong. The overlap operator obeys what's called the Ginsparg Wilson equation, which I'll get back to, which was written down in 1982. And Neuberger showed that his operator obeyed this equation in 1997. So in the continuum, chiral symmetry is encoded in this equation, which is that gamma 5 anti-commutes with d slash. The Ginsparg Wilson equation modifies that, and on the right side it has an object which is proportional to the lattice spacing and therefore goes to 0, the continuum limit, but has this peculiar structure d gamma 5d. Now, this is totally unintuitive why this is an interesting equation, but I think it's a little bit easier to understand if you multiply both sides by d inverse, which you can do in the case where you don't have, where the topology is trivial and d doesn't have 0 modes. So if you do that, then it says that the anticommuter commutation relation of gamma 5 with the propagator, which is has non-zero extent in the xy direction, is proportional to a gamma 5 times the unit matrix, which is the delta function, x minus y. So this tells you that the propagator behaves completely normally under chiral symmetry until you try to go from a point in space-time to the same point in space-time. So in fact, the modification to the chiral behavior is only seen when you try to look at matrix elements occurrence that are sitting right on top of each other. And that's the sort of singularity that is important for the anomaly. And in fact, this equation was derived as sort of the minimal violation of chiral symmetry you'd need on the lattice in order to reproduce the anomaly and nothing else. So let's try to see that a little bit more explicitly. So the big question is, well, the two questions are, does this give you the right anomaly? And the second question is, does it protect you against additive mass renormalization? These are the two things we know about from chiral U1 that we expect to have. So Boucher in 1998 showed that if you, very simple algebra, that if you have this operator and D obeys the Ginsparg Wilson equation, then it follows that this infinitesimal transformation is a symmetry of your action. It doesn't look like it should be. It's a chiral transformation that's modified by the sort of nasty derivative operator. But if you just stick this into this action, you'll find that the extra pieces that you get are canceled off by the D satisfying the Ginsparg Wilson equation. Because of this, this generates a continuous U1 symmetry, and it's violated by a mass term for the fermion, and therefore it's sufficient to guarantee that you'll get multiplicative mass renormalization. Now, you might say, oh, wait a sec, if a simple modification of the chiral symmetry becomes an exact symmetry in the lattice, then how do I get an anomaly? Well, the answer is that this is not a symmetry of the action, of the measure of the action, even on the lattice. If I look at the variation of the measure, I find that this goes like trace gamma 5d, and this is the index of the overlap operator. And if I stick in my formula, the overlap formula for d, this is just the trace of the sine function of h. So one thing that's neat about it is that, except for this factor of lattice spacing, this is always an integer on the lattice because this eigenvalues of this operator are just plus or minus 1. So this is the same thing that in the continuum turns into the difference in chiral modes, which becomes the twice the winding number of the gauge field. So one of the neat things about this is that you have a very well-defined index theorem on the lattice, and it always gives you an integer, even though the winding number of a gauge field is not an integer typically on the lattice and is very difficult to define in a way that's really robust. So this gives you an alternate way of defining topology on the lattice in a way that always gives you an integer. And this has been used then to identify interesting topology in the gauge fields. Is you look not at the gauge field, but you look at the solutions to the Dirac equation, look for zero modes. Now, if you look at the spectrum of eigenvalues, then you find that the case where you have non-zero topology in the gauge field is that you find that it's a little bit funny at first because the eigenvalues on the circle are paired plus and minus. And so it looks like, how would you ever end up with a mismatch in eigenvalues? And the answer is that non-zero topology, instead of merging together, whether both of them sit at this point or that point, they get split, and you have one at each of these points. So n plus and n minus are the values of, are the corresponding to counting the states that are at the special point lambda equals 0 with either positive or negative chirality. Being a lattice, they're always met with pairs of the opposite chirality, but they're not sitting at lambda equals 0, they're sitting at lambda equals 2. So this is sort of in eigenvalue space, the analog of what's happening with these surface modes being physically separated in space. So an instanton will put a plus chirality mode at lambda equals 0 and a negative chirality mode at lambda equals 2. And n plus minus just counts the modes at lambda equals 0. So one loose end still in this picture is I didn't explain how Ginsparg Wilson derived their equation back in 1982. They started with a chiral theory, Dirac theory in the continuum, massless fermions, and then they rewrote their theory by taking dividing space up into cells and replacing the fermions by averages over those cells. So they put an auxiliary field that was coupled to a Gaussian smearing of their fermion, and they integrated out the original fermion and asked, let's look at the effective theory of these Gaussian smeared lattice fermions. So it's a weird theory. It's got a continuum gauge field, but lattice fermions sitting on top of this gauge field. And the thing is, this is just a rewriting of the original theory, so chiral symmetry must still be there, and the anomaly must still be there. And so they then asked, what is the chiral transformation in this theory? And they ended up with the Ginsparg Wilson equation. However, they couldn't find a solution to their equation, and so this paper was lost for about 15 years. So rather than give you a summary, I'm just going to say that's sort of the picture now that we've got, and I'd be happy to answer any sort of questions.
For the chiral fermions, the vector current in 5D in presence of this topological term gives this anomaly on the walls. Is it possible to define a vector current on the walls which is conserved for these kind of formalisms?
I'm sorry, it's possible to what?
To define vector current which is conserved on 4D itself,
I'm sorry, I still don't understand.
Is it possible to define a vector current which is conserved on the 4D slice?
A vector.
Yeah, starting from 5D formalism.
Absolutely. So you want to put equal numbers of right-handed and left-handed modes on one side and equal number on the other. Yeah. So actually, I'll be talking about that tomorrow. That is what the condensed matter physicists call the quantum spin Hall effect. So that's a theory where when you turn on the electric field, the representation on each side is anomaly free all by itself. So you don't end up with any charge currents going through, but you do have global symmetry currents that are anomalous. And so you get transport of chirality goes across, but no electric charge. And so that's the analog of this condensed matter system where you have a Dirac fermion on each surface, and they have taken pictures of the Dirac cone. And then what gets transported across is spin in the non-relativistic system, but not charge. And so yeah, you can do that. It's a expensive way of doing Dirac vector-like theory, but it's an interesting one. You already went? True.
So you said that at some point people realized that you could just chop the space in half and just keep the part that keeps the current and throw the other part away. But you need some boundary conditions to make sure that things are okay, right?
Sorry, what?
You need some boundary conditions.
Yes.
So what do you do with that?
What do you do? Yeah, I think it's. I think people put in free bounded conditions, but it's a linear differential equation, right? The Dirac equation. You put the free condition on opposite sides for the two chiralities, I believe, so that you can have. Sorry.
Is this
talk to an expert?
Yeah, if I remember correctly, and I'll check if I don't. The Pauli-Villars term is, I believe, anti-periodic as you jump from one side to the other. It has a minus sign. And then the mass comes and changes that anti-periodic thing to the point where the infinite mass turns it into no, I'm saying it wrong. Okay. The infinite mass, I guess it may be, anyway, I'll tell you the answer, but I don't remember anti-periodic. The point is you put a mass term on the boundary. And at zero mass, it's fixed boundary conditions, that's right. And the Pauli-Villars, I think anti-periodic or periodic, doesn't really matter which. When the mass goes to 1, the Pauli-Villars term and the Dirac term become exactly the same, right? So they completely cancel. And so that bare mass term actually corresponds to infinite mass.
The way I would do it as an engineer is I'd go look at my solutions on the cylinder and make sure that I didn't cause mismatches of the Pauli-Villars and the Fermion and got rid of it.
It's just the hopping term. You have a hopping term from one edge, bang, to the other one. That's what it is.
I mean, I should mention that this, of course, wasn't the end of the story. Then there are all sorts of work on making this realizable on the lattice in a much more efficient way. You know, one of the innovations is this Mobius domain wall fermion that Rich invented. And before that, Shamir was the one who gave this finite lattice.
So can I think of the Shamir construction as essentially using orbifold boundary conditions? This is something that's always confused me.
You are.
Yeah.
Sorry. Sorry?
Is this the equivalent to saying I need orbifold boundary conditions, following up on what David was saying? If I go to this sort of Shamir construction.
Okay, I've not followed that.
This is something I've never kind of understood.
Okay. I haven't paid attention to it.
So you briefly mentioned about this magic when you couple sort of an electric field of very low frequency or long wavelength. You have a chiral mode here and a chiral mode there, and there's a whole massive region in between. I am also puzzled. Do you have a better explanation of what's going on? In some...
I think it is the sort of finite version of the Hilbert Hotel, which is that every particle moves over one. One of them comes in off the boundary, everyone moves over one of them pops off onto the other boundary. And this motion of everybody moving over actually doesn't cost a lot of energy, as opposed to making a wave where you have a higher density of states in one place and a low density elsewhere.
So if it's not an infinite separation, then the small mass sort of causes this issue?
Sorry, the what?
Suppose it's not the infinite hotel, in the sense that extra dimension was not infinite. Let's say we keep it finite. Then it's the small mass that will cause the trouble?
Cause what trouble?
Coupled to this electric field, is that what happens?
Well, I'd say that the states in here are very heavy. So
right.
So if I think of them as particles, trying to make them denser in one place and rarefied in another would cost a lot of energy.
Right.
But having everybody move over one does not cost a lot of energy. And that's what the electric field is doing. It's putting an extra one on one side and taking it out at the other, and everybody just moves over without actually exciting any of the heavy modes.
Yeah, I have a question which is really partly for stringy people. If you think of the Pauli-Villars and the Dirac as being a fermion and a boson, I realize it's got the wrong spin statistics, so it's kind of a kinematical thing, right? Then the domain wall is breaking that symmetry. And I believe in string theory, that's the way you also get chiral modes. You take a brane in a SUSY theory, and then you break the, you can break the SUSY theory, you break the SUSY symmetry on the brane wall, and you get a chiral mode. Is that true? I've always thought that was an analogous phenomenon.
I think it's probably the same equations.
What?
It's similar equations, I think.
Yeah, and so in fact, it means you could do something sort of weird. You could say, really take a SUSY theory, and don't try to cancel the fermions against fake fermions with the wrong statistics, but cancel them against actual bosons. And you would have another kind of domain wall fermion, which would be sort of more...
When I was thinking about supersymmetry on the lattice, I tried creating domain wall bosons, and it doesn't work.
It doesn't work, yeah. Okay. Okay, I've always been curious whether that would work.
It doesn't work means I was not able to find an answer.
Yeah, okay. Well, good, I'm interested that you tried. I still think it might work, but I don't have an answer either.
And not only that, but because I have a poor memory, I forget what my result is. I've tried many times, actually. Sorry, Noboro.
Yes, you mentioned the relation between the two-dimensional gauge theory and three-dimension through this Chem Simon. Now, if you just extend this formation to the four-dimension, you said that the five-dimensional Chem Simon, which is curvature to the third power is d times Chem Simon. That's what you usually use, right, as a Chem Simon. And then d is exterior derivative. So Chem Simon part is essentially a dA dA. Therefore, it's five dimension.
Yeah.
Now, suppose, but in this case, the gauge field is only one form. Now, suppose you can extend this formulation into extension of the Chem Simon with other differential form, including other differential form, not only one form, but other form. Then if one can just construct the formulation of the 5-dimensional Chem Simon, which is related to the 4-dimensional gauge theory, just like in 3-dimensional case, two-dimension. Could that be helpful for 4-dimensional? Because we have this generalization of the 3-dimensional Chem Simon into arbitrary dimension, so that 5-dimensional Chem Simon has all the degrees of differential form.
I don't know of any generalization that would give you a marginal operator like that. You don't want something that decouples as the bulk mass goes to infinity. So I don't know. I don't have a clear picture of what these operators are. So, but I suspect it won't be of use. But you should take a look.
Yeah. Okay. I want to discuss later, maybe.
Questions?
You have a nice description of the exponential suppression of residual chiral symmetry breaking in the continuum domain wall formulation. And when we look at this on the lattice, we know there's also these power law effects 1 over L that appear attributed to localized modes on the walls that are non-localized in the extra dimension. And I'm wondering if there are interesting things you can say about the connection between the continuum domain wall setup
correlated with rough gauge fields, or
associated with localized dislocations and sort of quasi-topological defects. So in the continuum, I'm wondering if these are related to topology and instantons and their connection to the domain wall setup, if there are interesting things to talk about in that context.
So I would have thought that these would be lattice artifacts that come from very rough gauge fields.
Yeah, I think I can answer this, and that is that when you change topology, an eigenvalue has to move through where you make this cut of mass. And so, of course, a real instanton would change the topology and the number of zero modes on each wall. But of course, in a lattice, there's always rough, little, teeny instantons that go percolating back and forth and really not smooth enough to be given the proper name of instanton, right? And it's an accumulation of all that rough stuff that is sort of topology moving back and forth in a jittering way.
So you're treating it as a lattice artifact.
Yeah, well, they're small instantons. You have a density of small instantons. Yeah, they're lattice artifacts in that sense. When they grow up and become big ones, they become real topology changing.
Yeah, going back to the condensed matter analogy, it's like having a dirty sample.
Exactly.
You can tolerate a fair amount of dirt, but not too much. So if you use I imagine if you use an improved action for the gauge, you'd see less of that.
Yeah, in fact, that's the problem. And naively, if it weren't for these lattice artifacts, you'd have an exponential convergence as you pull them apart. But in fact, there's a density of these, so they're linear convergence. And what Mobius fermions did is just made it into quadratic, just slightly.
And how does it depend on the lattice spacing?
No, they're always there. I mean, there's at any lattice, no matter what the lattice spacing is, you have a spectrum all the way up to the cutoff. See, you can never get rid of these.
Well, okay, what I meant is, how does it depend on the bare gauge coupling?
The smoother the configuration, I don't have to think about it. Yeah, there's a devil's bargain here that when you get too close to the continuum limit, then there's a barrier of topological change, right? And so you have a trouble sampling topology, and then probably you're okay, but you're stuck. And that's one of the.
I would have guessed that these specs would go like e to the -1 over alpha, where alpha is the bare gauge coupling.
Hello. Any other questions? I had a question, which is more a question about the state of the art now, which is how much have people done using these domain wall fermions or overlap, say electroweak theory? what is the current status of how much of electroweak theory can you do with this kind of formalisms?
So first of all, in the relation between overlap versus domain wall fermion, the overlap looks far more appealing because it has this exact symmetry, but it has 1/square root of h squared in it. Okay, so taking an inverse square root of a large matrix is expensive, and there are various algorithms for doing that. And ironically, one of the algorithms for how you would do that, it basically recreates the fifth dimension. Okay, and so there's no great time savings. If anything, I'd say the overlap operator is somewhat more expensive than the domain wall fermion. So people use the cheapest fermions they can, okay? So it depends on the problem you're trying to solve. So if you're not very sensitive to chiral symmetry, use Wilson fermions. If you are, if you require chiral symmetry, but and you're willing to put up with a lot of weird flavor stuff, you might use staggered fermions. If you want really good chiral symmetry for hadronic physics, you probably use domain wall fermions. If you really want to study topology of gauge fields and lattice, you probably would use an overlap fermion. And so it's just a question of cost. I think everybody would use overlap fermions if they had an infinite amount of computer time, but the actual use is different.
In particular, the chirality is important in electroweak theory for things like sphelerons and baryon number violation. Is that something that can be done in?
I'm sorry.
For baryon number violation, the violation of B plus L.
There's a problem there, which is that you want to do that in the standard model, and the standard model is a chiral gauge theory, and we do not have a theory for chiral gauge theories. So, you're going to have to settle for UN axial violation or something like that. Yeah.
So, but can you see B plus L theory in a lattice in a numerical simulation? Is that at the current state of things?
Is what?
Can you see B plus L violation in computer?
No one can study these really interesting problems that you'll physics that you'll see in a chiral gauge theory. Yeah.
Okay. Any other questions, comments? Okay, if there are no further questions, let's thank David again.